We started solving this question. Got pretty far. The idea is we want to try to isolate that u to the fourth. I'll raise those sides. Base E. Using algebraic techniques, the right-hand side you should see becomes just some new constant, c sub 2 times x to the fourth. U is y over x. Y to the fourth would be c sub 2 x to the eighth minus x to the fourth. Let's leave it like that. You cannot explicitly solve for y in this case, right? Because it's an even power. We'll say that's our solution. Show this is homogeneous, then solve. There is another way to show homogeneous. Set that as just f of xy. So if you have an equation in the form y prime equals f of xy, it'll be homogeneous if f of tx comma ty is f of xy. I'm actually going to use that method here. Because what that's going to boil down to is we're showing the numerator is homogeneous of some degree, denominator is homogeneous of the same degree, which means your t to the opposite going to cancel out and you're left with the original function. Because we're at right now, right? Factor out that t squared. And we'll just get back to the original function. Hence, the equation has to be homogeneous. This allows us to use that substitution. Use substitution y as ux, y prime within the u plus x u prime. For homogeneous, that's always going to be the case. Again, you could use, what was it, x over y equals v. So you could also use x equals v times y. But then that's going to give you x prime instead of y prime. That's the left-hand side. Right-hand side. That should be a minus. To u over 1 minus u. Sorry, squared. Subtract u from both sides. We want this as a single denominator. U minus u cubed over 1 minus u squared, right? Separate it. 1 minus u squared over u minus u cubed du is equal to dx over x.
Is it plus u cubed?
Should be plus, yeah. that integral more interesting. That left-hand integral, how would you go?
You just make it 1 over x dx. And then,
Left-hand.
oh, the left hand.
Right-hand is easy.
Yeah.
You should do that with left-hand if you're a backhand.
Quotient
Rules for Calc 2.
rule.
There's no quotient rule in anti-differentiation.
Integration by parts.
You can try.
Partial fraction decomposition.
This is a partial fraction
Yeah.
decomposition problem. This is an integral of a rational function. It's already in proper form, which is nice. That means you don't have to find its decomposition. I think I'm not bad. Thankfully, this is not a Calc 2 class. So I'm just going to integrate this one. Menu, calculus, integral. It's an antiderivative, so I don't need bounds. And it was 1. I'm going to need parentheses. 1 minus v squared divided by v plus v cubed. Now, when you're doing powers with the caret in this calculator, be careful. Notice that the cursor is still in the exponent. So you can either hit tab to get out of it, or the right arrow. And you don't want it to keep writing out your equation, because it'll all be in that power. Tab again with respect to v. Enter. There it is. And notice we don't need the absolute value on the v, or in the denominator, right? V squared plus 1 will always be positive. But technically, it's the absolute value on the whole thing. Now we need to solve for v. I'm fairly certain it's not going to be possible to fully isolate v, but at the very least, maybe get that. guess we could multiply numerator and denominator by x squared. Write that. I don't know how much nicer we're going to get it. And so remember if you have x squared, you can put x squared inside of an absolute value. Because x squared is always positive. Which is why I was able to simplify the y over x inside the absolute value. If that was, say, x cubed, I could not have done that. X cubed does not necessarily equal the absolute value of x cubed. Yeah, I think that's as nice as it's going to get. Unless you want to move the minus c1x, absolute value of x, and write it all equal to 0. Which you could do. For the sake of space, I'm not going to do that. I'm just going to do it like that. I should have enough time. But just to be safe right now, I'll skip this one. And it's just homogeneous with IVP. Because I want to cover the two Bernoulli equations. And then if there's time, I should have time. If there's time, I'll come back to this question for you. All right, so remember what Bernoulli equation is. And I don't have it on this set of slides. All right, but Bernoulli equation, any equation of the form y prime plus p of x times y is equal to q of x times y to the n power. Well, n is 2. So this is clearly Bernoulli with n equals 2. The substitution that we use, u equals y to the 1 minus n. We're going to use y to the minus 1. Y would then be u to the minus 1. Then take its derivative, negative u to the minus 2, and then chain rule times u prime. Now make the substitution into the equation. And what you should find is once you make that substitution, you get a linear equation in U. Multiply through by a negative u squared. It is now linear in u. And we know how to solve linear equations. What do we have to do?
Integrating factor.
Which is what? In general, not just for this problem. How do you find the integrating factor?
E to the integral of p of x dx.
So what is our integrating factor here?
E to the integral of x dx.
What is that antiderivative?
E to the x squared over 2.
That's the integrating factor. You multiply through by that, right? And if you remember, that will always lead to the derivative of your integrating factor, in this case times u, is equal to the right-hand side times your integrating factor. How would you evaluate that antiderivative? Alright, I need to adjust something. Actually, I need to adjust two things. I multiplied by a negative, didn't I? Yeah, I didn't change any of the signs. No, that's just plus. This is what I multiplied by the negative. Just a slight change. How would you evaluate that antiderivative?
So,
Change a variable. Don't use u sub here because we're already using u. V, some other letter. Yeah, that's just a simple change of variable. And V, negative x squared over 2. dv is negative x dx, which we already have. That just simply becomes e to the u du, or e to the v dv, right, which is e to the v. Multiply by e to the x squared over 2. U equals 1 plus c e to the x squared, x squared over 2.
Don't you have to multiply the entire integral by the negative? That was outside the integral.
Already accounted for that.
Or you did.
When you do change a variable with negative x squared over 2 as your v, that derivative is negative x dx.
But the c is not negative?
Well, maybe, depending on the initial condition. But even so, I wouldn't distribute that negative through because that negative should actually be inside with the negative x. So I took that entire negative x dx as my dv. So it's just e to the v dv. That's the antiderivative. And what was u? Y to minus 1, right? What's y?
we 1 over that.
1 over that. Or if you wanted to, keep it as a negative exponent. Either one's acceptable. This one's easy enough, probably looks nicer to write it as a fraction. but maybe some that probably look nicer to leave it as an exponent. So either of those would work. Good. Is this Bernoulli?
Yeah.
And that is Bernoulli. Is it?
Yeah.
Yes. What's N? Or not X, sorry. U is Y to the 1 minus N. That would make Y U to the 3/2. Right, then it's Y prime being 3/2, U to the 1/2 U prime. Now make the substitutions. That should be U to the 1/2, right? U to the 3/2 to the 1/3 power. Multiply through by 2/3 U to the minus 1/2. Three-fourths times 2/3. Half. You should just be left with a U, right? U to the 3/2 times U to the minus half. Two-thirds X to the 4th. Once you've established it's Bernoulli, you get to this point, you can determine if you're on the right track by looking at that and saying, is that linear in U? If it is, you may be on the right track. If it's not, then you definitely know you screwed up. Either you screwed up with the substitution, when you actually put the substitution in your algebra, or you're using the wrong substitution. One or the other. Just because you get to this step and you go, that's linear, that doesn't mean you were right. You still could have screwed something up and just got lucky. What's our integrating factor?
Or -1.
That's P,
Oh, U to the integral is -1.
which is what?
Negative X, -1/2 X.
E to the negative X over 2 would be our integrating factor. How would you evaluate that antiderivative? Why did I write just x? How would you do that?
By parts.
How many times? Yeah, you have to do integration by parts 4 times. All right, after the first one, you're going to be left with an antiderivative involving x cubed times e to the negative x over 2. That means you're going to have to do it again. And you're left with an x squared times e to the negative x over 2. Those are going to be constants in part. So you're going to have to do it again. Which means you're going to be left with an x e to the Joe. Yes. You need something. Oh, okay. Sorry. Something you picked out yet. Pop quiz. No, he's leaving. I could, right? And everyone gets an answer here. Yeah. If you want to do that by hand, I won't stop you. I have time for that. And so again, thankfully, this is not a Calc 2 course. Actually, I think I should do this one on both of them to show you how to do it. Integrate. Now you're integrand. Said it was 2/3 x to the 4th times 2 ways to use the e function. Could just do a capital E raised. So capital E is just your natural number, or exp brackets then what the power is. I prefer this method. It was x over 2, right?
How big of it is?
Comma with respect to what? X. And then x cubed. That's what you get if you did integration by parts 4 times. So again, I won't stop you. Oh, you know what? I'm also going to back out a negative. think that can be simplified any further. That's what full simplify does, it's just gonna fully simplify it. Which for a lot of, especially when you're dealing with trig expressions, I recommend you do. It will leave sine squared plus cosine squared. It'll just leave that when it's actually one. Whereas you do full simplify, it will use the trig identities and simplify. And all that percent is it's just recalling the last output. No, that looks even worse, so yeah. No, I'm not gonna use that form. But that's what full simplify does. You also have just regular simplify, but I don't ever use that one. Simplify doesn't always fully simplify. It may leave out certain properties. Again, the easiest way is it may leave out certain trig identities. So I always just use full simplify. I think full simplify will also try to get rid of hyperbolic functions if possible. Or that you may have to use trig to exponential to do. We'll get there. I'm fairly certain I'm going to have to use that command in this course. Now multiply by e to the x over 2. And u is what? Y over x? No, I'm sorry, that was something else. U was x to the 2/3, right? Or y to the 2/3. Power of technology. Why would be that whole thing to the 3s power? Good. As you can see, some of these solutions can get pretty hideous. Yeah, I'm not going to have time to fully complete that. I have 5 minutes left before I want you to work on the group case stuff. We'll just walk through, right? Show this homogeneous, we're going to do that. It's clearly homogeneous. Use the substitution y equals u times x. Go through all that. You find your general solution like we did in the previous problems. Should be a lot of work. We get down to your general solution, then just apply the initial condition to find C. That part's easy. What you should get, I'll let you do the work on your own. I'm hoping my work is right on here. Shape that. Once all is said and done. That actually concludes first order equations. That means what we look at next, modeling the first order equations. It's broken down, well, this textbook doesn't really do it, but generally it's broken down into two types of models. You have your linear models and your non-linear models. Linear models are way more common, at least for first order. There are also other techniques that I'm not covering. A lot of the equations that you run into in applications cannot actually be solved. You have to numerically solve for it. Right? So you have your numerical techniques. One of the most common is the Runge-Kutta method. I'm not even sure if your book covers that. I can't imagine why it wouldn't. It does, it's chapter 3. So you have Euler method. Then you have the Runge-Kutta method, and if I remember correctly, there's actually several levels of Runge-Kutta. Trying to remember back when I took numerical analysis. I know of at least two. There's a Runge-Kutta 2 and a Runge-Kutta 4. I think there's also a 6 and 8. I can't off the top of my head remember what they do. I think it has to do with precision. The higher the number, the better the precision, but also the more work that's involved. That requires coding. Again, I'm not really going to cover it. Maybe if I have time at the end of the semester, I'll revisit it. Go back and kind of show some coding with Runge-Kutta. But for now, we're going to skip it. And all of the equations we're going to look at can be analytically solved. All right, so get into your groups. I thought they scared you off.
No, I was in Vermont for another class. Oh.
We'll work on this for half an hour. Break. It'll be 2:25. We'll start looking at the models. Okay, so we're going to be looking at models. I'll let you read through these slides on your own. It's just discussing the different kinds of models we have. Half-life itself is interesting. Right, Newton's law, cooling. I want to mention something about half-life. And so the half-life of an object is how long, or I shouldn't say half-life of an isotope is how long it takes that isotope, half of the amount to decay. And so what's carbon-14? That's like 5,400 years, something like that. It means after 5,400 years, half the amount of carbon-14 remains. After another 5,400 years, half of that amount remains. How long would it take to fully decay? Just give a number. Say we have 5 grams carbon-14. Again, we're going to use a half-life, I think it's 5,420. Which is say about 5,400 years. How many years would it take for there to be 0 grams? That's what it would mean to fully decay. Infinite. It gets cut in half every 5,400 years. So first 5,400 years, you have 2.5, right? Next 5,400, you get half of that, 1.25. Then half of that. Then half of that. It never actually gets 0. No, half-life itself isn't infinite. How long will it take for the isotope to fully decay? That's always infinite. So once any kind of radioactive isotope is introduced into the environment, it's there forever. It's just a matter of how much is there. Carbon dating, that's Newton's law of cooling. Series circuits, we will be re-examining these later. These are just first order circuits. And Kirchhoff's laws. If you've had E&M, you're familiar with them. And this is an LR circuit. And this is an RC circuit. When we do second orders, we'll look at LRCs. Again, you have your equations there. So read through all this at your leisure. Population dynamics. And then logistic equations. Logistic function is the solution to logistic equation. Just to make sure I have enough time, I'm actually going to start with 7 and 8. These are the mechanics problems. This one is free fall. And so if you remember from your introductory mechanics, you know what free fall is. You ignore air resistance. The next question is going to actually include drag air resistance. Body of mass, 5 slugs. Why are they using that measurement system? I don't know. Thought that's why we fought the revolution. But yet here we are. Drops from a height of 100 feet with 0 velocity. Assuming no air resistance, we're going to find an expression for the velocity of the body at any time t, an expression for the position and the time required to reach the ground. Let's say it's going down like that, and this is the ground level. We'll say that represents y equals 0. Means up here would represent 100. We know the mass. It's 5 slugs. We do not have air resistance. Which means all we have is dv dt is negative g. It's in free fall. Acceleration is just due to gravity. We also have initial velocity is 0 feet per second. That is our initial value problem. No, that's just really easy to solve. Great. This is essentially a Cap 1 IVP. V is negative GT plus some constant. But we know that V of 0 would just be what? C? And that has to equal 0. There's V of T. What's G, by the way? For this problem. What's the units for that?
Oh, that's weird. It's 32.2.
So about 32 feet per second. Yeah, I'm just going to leave it as little g. Is little g constant? Little g is actually a function of height. It's not always 9.8 because the force of gravity depends on how far away you are from the sun of the earth. So the higher you are, the less it pulls you down. Specifically, it's an inverse square relation. That's just, you want to lose weight, just go higher. Increase your altitude, decreases your weight. Don't get into this argument with me. There's no way to lose mass, unfortunately.
Yeah.
You can gain mass, though.
Mm-hmm.
So that's the function for V. We want position of Y. Well, we know that dy dt is velocity, right? And we just found what velocity is. We also have an initial condition. What's y of 0?
$100.
100. We're dropping it from 100 feet. So initially you have a height of 100. There's our initial value problem. Again, that is a really simple initial value problem to solve. Negative 1/2 gt squared plus, call that C1. We use the initial condition. So that C1 would have to be 100. Okay. There's your position function. And just re-deriving what should have been derived in intro mechanics. You should have derived your free fall model. Y of t is y naught plus v naught t minus 1/2 gt squared. Y naught your initial height, v naught your initial velocity. It also wants us to do what? Find how long it takes to hit the ground. When it hits the ground, what's y? Stop right there. Half gt squared has to be 100. T squared would then be 200 divided by g, right? For our purposes, time is non-negative. So we take the positive root. Square root of 200 over g. That is the exact time. If you use the approximation of 32 feet per second for g, you're going to wind up with that being about 2.5 seconds. Free fall, pretty boring. Nothing really interesting in free fall motion. This is the more interesting problem. Body of mass m thrown vertically into the air with an initial velocity of v naught. If the body encounters an air resistance proportional to its velocity, we want to find first the equation of motion in the coordinate system where the ground is represented by y equals 0, an expression for the velocity of the body at time t, and the time at which it takes the body to reach maximum height. So start again with a diagram. Right, there's our ground level. Setting it so that that represents y equals 0. An initial height of y naught. And it's thrown upwards with an initial velocity of v naught. There are two forces acting on it. We have the force due to gravity, but now we also have drag. Which is going to act in the, I'm sorry, we're throwing it upwards, sorry. So it is downwards. Drag acts in the opposite direction of motion. And so once it reaches maximum height and starts to fall, your drag flips. So this isn't even falling. We're ignoring that part. Force due to gravity, negative mg, right? Mass times acceleration. They told us that the drag is proportional to velocity. That simply means that drag is some constant times velocity. K is a constant of proportionality. In this case, I think it would be called the coefficient of air resistance. The amount of air resistance that an object feels is a function both of your speed and surface area. I think you've seen skydivers, you're familiar with that concept. Increase your surface area, you're increasing the drag. So you're going to slow fall, or you're going to fall slower. You decrease that, you're going to begin to fall faster. Either way, you're still going to reach what's known as terminal velocity. And that, again, depends on the surface area. Terminal velocity is much slower if you have a larger surface area. But the terminal velocity is the point at which the drag cancels out the gravity pull down. So they're equal in opposite directions. That's your terminal velocity. Total force. Sum of forces. Negative mg times or minus kv. On the other hand, total force has to be ma for this problem. That's Newton's second law of motion. Sum of forces is mass times acceleration. But acceleration is what? What is acceleration? Of what?
Velocity.
Change in velocity. So what we're actually doing is we're going to wind up doing B first. Because in order to find a function of position right now, we have to first. Later we can jump right to position. This would then be a second order differential equation with respect to y. Right? Because velocity is the derivative of position. Right, but for now, we're dealing with first orders. So we have to solve that. What kind of equation is that?
Linear.
That's linear. That makes it really easy to solve. I'm really sick of writing DBT. You familiar with dot notation? Good. We have to divide by n, right? Call it mu sub I to represent the integrating factor, not air resistance. What is our integrating factor? Which is what?
kv over m, e to the kv over m.
K what over n?
Kt over m.
How would you do that antiderivative? Keep in mind, we're making assumptions that both G and M are constant.
Change variable.
Yeah, this is just simple change variable. GM is not really the order that we typically write it in. Write it that way. Multiplied by e to the negative kt over n. Let me get that. Use the initial condition. V of 0 is V naught. V of 0 C minus mg over k, right? That has to be V naught. Makes the constant V naught plus mg over k. Minus, yeah, mg. Okay. There is the velocity model. Actually, I'm sorry, I misinterpreted A. That's the equation of motion. So the equation of motion was just the differential equation. We're not looking for position. For some reason I was thinking it was find an expression for the position. So that was part A, and then we just did part B. You could easily find a model for its position, right, by now saying that V is dy dt. Solve. Right, you integrate both sides. And you get your y of t. And then use your initial condition for height, y of 0 is 0. Last thing we have to do, right, is determine the time at which the body reaches maximum height. So how long will it take to reach maximum height? Well, what do we know about velocity at maximum height? It's 0. Now we solve for t. two things at once. I'm going to isolate that exponential function. I'm also going to clear out the fraction because we don't like compound fractions. Natural log of both sides. We get t is negative m over k times log of mg divided by k v naught plus mg. Does that answer make sense? But we know that m is always positive. V naught we know is positive because it's being launched upwards. If that natural log is positive, k would have to be negative. But if we assume k is positive, that's a natural log of something less than 1, which is negative. Negative times negative is positive, times positive. Chances are k is positive. So yes, the same thing makes sense. We're not getting negative time out of this. I could rewrite this. I'm using moles and logs. It just looks even worse in my opinion, but that is the amount of time it would take. Right. The important thing to note here is the air resistance. Adding the air resistance into consideration. If it is an object just falling, that resistance will always be proportional to velocity. So it will always be of the form kV. You just have to determine is it positive or negative based on the problem. If it's falling, remember, your air resistance is in the opposite direction. It's always in the opposite direction of motion. Good. Now that the mechanics are out of the way. Person places $20,000 in a savings account, which pays 5% interest per year, compounded continuously. How much is in the account after 3 years? And how much time is required for the account to double in value? All of this is under the assumption that there are no additional deposits or withdrawals. Remember that capital P of T represents the value after T years? Right, dP dt is rate of change. Right? How much has the value changed with respect to time? Well, the account gains 5% per year. Just be that, right?
It's compounded. Continuously, is that not affected?
If it wasn't compounded continuously, it would be a problem. And we know P of 0, right? What is it?
20,000.
There's your IDP. Solve for P. But what kind of equation is this?
Linear.
It's linear. No? No, it's not homogeneous. It's also separable. Doesn't matter which way we solve it. We're going to try and solve it using separable. We're going to get dP over P equals 0.05 dt. This means that natural log of P is 0.05 t. Notice I don't have the absolute values because P is always going to be non-negative. Plus C. You get P is some constant times e to the 0.05 t. Using the P of 0, just gonna get C1, right? Just 20,000. We get 20,000 e to the 0.05 t. Does that match the compound interest formula you learned in calculus for continuous compound? Yes, it does. P equals P naught e to the RT. That's where it came from. Because this is exponential growth. That's what compound continuously means, right? Exponential growth. And that model was given up here. It's proportional to the amount. In this case, our K was the interest rate. That answers the first part. How long is it going to take to, oh no, wait, I'm sorry, that doesn't answer the first part. That's just to get to the model. Now we can answer the first part. How much is in the account after 3 years? $20,000 e to the 0.15. Since we're dealing with money, we can approximate this. How many decimal places are we going to keep? 2. So 2 for money. Don't forget units. It's going to be about 23. 236.68. So about $23,237. After 3 years, you're only getting like $3,200. Of course, to be fair, your initial deposit wasn't that much anyway. So. Although if it is a savings account, 5% interest per year is a really, really, really good account. Like that's God tier savings account. Oh my God, what are most banks? 0.01% a year. Even most money market accounts, I think, only 2 or 3. So 5% is a God tier for savings. However, for investment accounts, 5% is garbage. My investments easily do 25% a year. How long is it going to take to double? Well, that means we want P of T to be 40,000, right? That means we need e to the 0.05t to be 2. .05t would have to be log of 2, or t is log of 2 divided by 0.05. Which is 20 log 2. Log of 2 to the 20th. 2 to the 20th is a really, really large number. If we're keeping it just in years, it's about 14 years. So with this savings account, you can expect your account to double in value every 14 years. After 28 years, you would then have 80,000. 14 and 28. 42? 42 years, it's now 160,000. You're never gonna hit $1 million unless you live to be over 100. There's only one way to decrease doubling time, and that is to increase your interest rate. Larger interest rate, shorter doubling time. S&P 500, I think, it's about 12 years. 10 to 12 years doubling time. Something like that. Lifetime S&P is 10% a year. So you just replace 0.05 with 0.10. Notice actually, the original amount is irrelevant for doubling time. You're always going to wind up with your e to the power has to be 2 for doubling time. So it's purely on the interest rate, not the amount. I guess the fun one, where the interest rate actually changes. I kind of don't want to start and then have to stop. So I'm going to say this will pick up. This will pick up on Thursday. I'll see you then.
You have time?
No, I can just go drop it off.